Welcome everyone. Okay, now it's working. Okay, in the last class, we briefly looked at the basics of quantum mechanics. Okay, we started with a brief history, okay, how this field essentially evolved. We started with black body radiation, photoelectric effects, okay, and then atomic spectra, then Compton effects, okay, de Broglie's wavelength, and Davison-Germer experiment, and many others. Okay, so from this we understand that this is very important to understand the behavior of subatomic particle, and particularly essential for us. The reason is that as device size is getting smaller and smaller, now it is approaching quantum limits. So this quantum behavior, quantum phenomena will emerge. Okay, yeah. So we also looked at very basic things. So for example, you are already aware of 3D vectors. So we just wanted to expand that idea. So 3D vectors to n-dimensional vectors. Okay, things looks familiar except for one thing, which are the basis vectors. Although the notation is now different, this arrow is now replaced with this bracket notation. Okay, yeah, so we defined how to describe magnitude. So essentially, whenever you see this type of bracket notation, there are two things you need to, two or three things to remember. So first thing is that, so this notation is a ket vector. So this is n cross 1 column vector, right? And complex conjugate of that is called prefactor. That will be rho, right? Yeah. So 1 plus n rho vector. That's all. So I mean, whenever you see this vector, it is a complex conjugate. Okay, that's point number one. So we needed to define basis vectors. So here you were aware of the scalar or dot products, right? Similar concept we also have, we just generalized it. So essentially here you say that if the dot product of 3D vectors, whenever it becomes zero, you call them orthogonal vector, right? So same thing we can also do for n-dimensional vectors. So whenever this dot product vanishes, so we refer that vector as orthogonal vector. And the magnitude, if that is 1, okay, then we call it orthonormal. So orthogonal plus normal, okay? Okay, so this is how we define normal. So here you see that when we are doing inner product, we call it inner product. So this essentially gives 1 cross n and n cross 1. Finally, we'll have 1 cross 1. Okay, that means we'll get a value. Okay, yeah. So another thing I mentioned that if we do linear operations, for example, scaling, addition, subtraction, multiplication, whatever, still it will belong to vector space. Okay, for example, if I take a vector and if I multiply that with 0 with a scalar, we still get a vector, but that vector is null vector. Okay, there is nothing in that vector, but that should belong to that same vector space. Okay, so these are the things we were not that careful. We were not that careful here, right? But this is the fact. Okay, yeah. So there were many homework problems. I hope you have seen the extended lecture notes and also some problem states. Okay, I think I have uploaded 2 sets of problems, like 20-25 problems each. So it looks like, I mean, there are many, but they're actually simple. So simple matrix operation, finding eigenvalues, eigenvectors. So very simple, just to, I mean, okay, to brush it up. Okay, nothing that complicated. Okay, so this is what we have. And then we discuss operators. So I said that if we have, here we are not dealing, I mean, very complicated things. Okay, I'm not, I mean, explaining the real, I mean, the linear vector space. Okay, but just giving you some examples. If we have this type of matrices, then it is like an operator. So this operator essentially operates on a vector, say ket, and we get another vector. Okay, so that was an example, and I gave you some examples of operators. For example, if we want to operate something rotate 90 degree, that means we are talking about rotational operator. Suppose we want to scale a vector, that means it's called scaling operator. So all types of operations here. Okay, but note that there are some operations which you can relate, which are observable. Okay, for example, 90-degree or some rotation, right? That is physically possible. So that defines observable quantity. Okay, and in that case, this operator should be Hermitian. Okay, Hermitian meaning is complex. I mean, H equals to H complex conjugate. And whenever you have this operator, you can sometimes we can have this eigen value problem, and so I can give you 2x2 or 3x2 operators or matrices. You can find corresponding eigen values, eigen vectors that we have discussed, right? And whenever those vectors are linearly independent, we can actually diagonalize the matrix. Okay, so these are the old concepts, but we are again brushing it up. Conceptually fine, simple maths, right? These are the things already there in the GATE syllabus, so you must have done it, right? Okay, but the key thing here is that we will connect these two quantum mechanics, and essentially you understand like how what is the application of this linear vectors. Okay, yeah. So then we moved on to this basic postulates of quantum mechanics. So there were three. So first is that defining something, okay, quantum mechanically, which will represent a particle. So that is defined by a wave function, okay. So we need a wave function. So we discussed what is this about? There's a probability density, okay. Yeah. So now here the wave function we can represent in terms of, so there are two forms. One is that the functional form. For example, we can have continuous wave, okay, and then we can decompose that in Fourier series, okay. These are, you can think about that, okay, think in terms of that, okay. There are different Fourier components. Another way is that it is nothing but in the discrete space we can think about linear vector, okay. There are two ways of representation. Sometimes we use this, sometimes we use that, but same thing. So one version is a discrete form, another version is a continuous form, okay. That's all, okay. Yeah. So now okay, now you understand this u1 or whatever we have shown here. These are basis vectors, okay. For example, in 3D you had xyz, some sort of that, and you know what is the relation, how to find the basis vectors. And I mentioned that this wave function, this particle exists in the space. That means, so if I take norm of that, okay, so that should be 1. So this is called normalization. It should be normalized. So whenever we have the wave function, we should be able to normalize it. That means it exists in the space. Okay, normalization, again, you think about doing this, taking this continuous wave or discrete form, okay. You know how to take the normalization. If it is psi, you can consider A and B both are psi, okay. So this will be like C1 squared plus C2 squared, stuff like that. So these are the discrete summation, and when you integrate, so it becomes like that. That's all. Okay, this was the first postulate. Okay. The second postulate is, okay, so fine. So this is how we can define a particle, but exactly how to find this wave function. Okay, Schrodinger came up with with this idea or with this concept. So just like the way we have Newton's equation describing classical particles, similar way we have Schrodinger equation. Okay, right hand side and left hand side. In left hand side we had the time evolution part, and right hand side the space dependent part, as we assume that V, the potential, is function of space, okay. And thereon I mentioned that if that is the case, we can try this wave function. That always engineers and physicists try. You try something and see if it works out. If that works out, then it's fine, okay. Here we tried that, okay, this wave function contains space part and time part. You just split it and see what happens. See what happens meaning you put this back to this equation and see if it makes sense or it becomes something impossible. Actually it makes sense, okay. So then you can, so that you can just work out. I think in the extended note I think I have derived it, okay. So you should go through that. So there's a time evolution part. So if you solve it, we get only a phase term. That's all. Okay, now this is called time independent Schrodinger equation, okay. And this first term is like energy. This first term is, we'll see that it represents an operator for kinetic energy, and this is for the potential energy. And so in today's class, we will see, we will take different case studies. We'll take different potential profiles and see how does Schrodinger equation results, okay? What Schrodinger equation results, okay? Yeah. So now you understand how to find psi, okay? Essentially, you need to solve this equation, time dependent part, time independent part, and there are different potential profiles, okay? That was the postulate 2. Postulate 3, we did the board work in the last class. But I have summarized here. Also, it is there in the notes. Okay, in 2 minutes. First of all, we mentioned that for observable, we must have matrix. Okay, so this is some operator, and if it is observable, then it must be Hermitian. Because if it is non-Hermitian, your eigenvalues will be imaginary. Then it is not observable. Okay. So we must have Hermitian. Maybe I can give you a matrix in the quiz and tell whether it's Hermitian or not. I will not tell whether it's Hermitian or not. Whether I mean, questions can be whether it will lead to any observable quantity or not. Okay. Then you have to figure out this. So you have the operator. So the moment operator is given, the thing should strike to your mind, eigenvalues and eigenvectors, right? We worked out these problems. Now we have the operator and it will be operated on a wave function. Okay. The question is what are the possible outcomes? These are the things we discussed, we did the board work. Okay. The possible outcomes are the eigenvalues. Okay, if you do one measurement, I mentioned that there are two possible measurements. One is a single measurement. Generally, this is very much related to quantum technology, single photon detection. Okay, single measurements are crucial. And sometimes rather doing single measurement, you do ensemble and find the average. Okay, so if you do single measurement, okay, then you will get one of these possible outcomes. For possible outcomes are here lambda 1, lambda 2 to lambda n, different types of, different eigenvalues. One of the possible eigenvalues you will observe after a single measurement. And no matter what wave function is there, okay, so after that measurement, the wave function will be collapsed to that particular eigenstate. This is very much important. Okay, yeah. So now this is how we can represent wave function. Okay, we have discussed, but there is no, so here this is written in terms of U1 basis, some basis, right? So we have seen this choice of basis is not unique, so we can have different sets of basis. So now it is your job to define this wave function with the basis of this operator. So this operator, meaning you should represent in terms of the eigenvectors of these operators, which are omega 1, omega 2. That means you need to do basis transforms. So there are ways. So in exam or maybe in your homework problem or what is that in that lecture notes, you see that very simple problems are given which you can do with simple algebra. Okay, simple stuff. So because I don't want to do you complicated analysis, I just want to know whether you understand the concept or not, right? But you got the point, right? So if you represent this in terms of that, okay, you can also represent in terms of these basis vectors. At least you can relate these to crystal structures, right? We have seen different types of basis vectors we can take. Okay, there is no unique choice. Yeah, then okay, here the question is, so if you do one measurement, what is the probability of occurrence? Okay, so that probability lies here. So it will be, so now if you represent this wave function with this basis, so whatever coefficient you have, so this will be the probability. Meaning, so if you are doing one operation, you will measure one of them with this probability. Okay, so if you do 1,000 or millions of exactly same measurement on identical system, then sometimes you will measure lambda 1 with some probability, lambda 2 with some probability. Okay, but you can average things out. Okay, and when you average, you get the expectation value. That's the difference. Okay, this is the expectation value. What I'm doing, I'm just averaging it, right? So we have seen, so averaging means this here we have lambda I, okay, lambda 1 modulus of d1 square, lambda 2 modulus, okay, stuff like that, and I can take d1, d2, so like d star here and there. Okay, that means essentially this is a matrix multiplication. These are the matrix coefficients. So I can represent this in terms of this bracket notation. If you are not comfortable, it is very easy. So take this, take some matrix 2 cross 2. So here what do you have? Say 2 cross 1 row vector, right? And here you have 1 cross 2. So finally, after doing this, what do you get? Okay, that makes sense. So yeah, so eventually this is the expectation value. Now there are different variants possible. I can give you matrix. I can give you matrix and I can give you row vectors, okay? And from there you can find this expectation value, or it can be in the continuous waveform as well. Okay, then you have to take the integral, right? So I think there are plenty of homework problems are given. You okay, solve them, practice it. Okay. Yeah, this is the thing. These are the things we discussed in mostly we discussed in last class. Now here there are some examples of operators. Suppose you want to know the position of a particle. Simple X. If it is 1D, if it is 3D, you use R. Okay, if I give you operator, you just put X here. The wave function is given. You do this integral. You will find something. Okay. Now momentum. This is called momentum operator. Okay, so if I ask you to find the expected value of momentum, you just use here and see what you get. Kinetic energy similarly. So if this is momentum, do you understand this will be kinetic energy? Okay, kinetic energy is half mv square or half m square v square by m square v square meaning p, right? So p square by 2m. Okay, is it fine? So this, okay. Now, if you look at the Schrodinger equation, so we have this term. So Schrodinger equation by default taking care of this, okay? And we can have defined potential profile. We'll just work out some cases, 3 cases, okay? Today, then you will actually know how to solve. But overall, is the idea clear? That's the point. Is it okay? Yeah. Next step is you need to solve problems. More you do, better it is. Okay? So if you read any other quantum mechanics books, you might get puzzled here and there what to do. That's why I have been typing continuously. And now you have enough number of problems. Okay, with that, more or less, you will have a very good idea. Fine? You are solving it? Always always do it yourself. If you ask AI will give you answers in 1 minute, but that will not help you. Okay? I mean, you can check. I have, anyway, I can upload the solution. We will upload solution. That's not an issue. But anyway, if you just put this, I ask AI, you will also get the solution. But anyway, you can check whether you are on right track or wrong. Okay, but you should solve it on yourself. Okay. Anyway, this was a summary in the last class. Any questions? Okay. Okay. By the way, I will have um, okay, we will discuss on the exams. Okay, exam topic after the class. Okay, maybe we can have a deal, and we'll try to have some negotiation. Okay, yeah. I mean, I can take exam. The question papers are already set, but that's for you. Okay, yeah. Okay, so today's class, acha, this is also something important. I thought I'll discuss it. Anyway, we have not discussed it. So previously we talked about postulates. Okay, but anyway, I think by that time already you have appreciated that already you get to know that the things are probabilistic. So probabilistic meaning we should talk about expectation value and standard deviation mathematically, right? How you define, right? Yeah. Now, actually, this probability is by default there in the system, in all the systems, but in macroscopic domain we just don't appreciate it. For example, let's take. Did I discuss it in last class? Did I? But anyway, we just spent 1 hour maybe. Okay. Suppose let's take a wave. This looks like a sine wave. Okay, electrical engineers are generally comfortable taking sine omega t as a function of t, but that t is a variable. I can take kx, right, in space. Okay, so do you agree that these are the frequency components? So when we have wave, either in time domain or some domain, wave meaning, do you know what the position of this wave? It is there everywhere. It is there everywhere, traveling like superhuman body. Okay? Today in India, tomorrow in UK, someone, okay? Everywhere, delocalized. That means when you know when you don't, but here the frequency is known. Okay? Frequency is known, right? That is omega because there is only sine omega t. Okay? That means if you know the frequency properly, then you don't know the position. That is natural. Now there is no quantum mechanics at all. Okay? Or we can have the vice versa. Okay, so now let's have something localized in time or space domain, maybe pulse, because electrical engineers are familiar with pulse in signal systems. When you do the Fourier transform, you get sync. So this is more or less localized in space. I could do Dirac function, but pulse generally electrical engineers are more familiar with. Okay, so it is nicely localized, but its reciprocal space is quite messed up. Again, we lose the information here. Okay, so it is naturally, fundamentally, this. So there is this uncertainty. It is always there. Okay, now, yeah. So one thing, so you might have seen in various experiments that momentum is inversely proportional to lambda wavelength. For example, take the Compton experiment. Okay, what kind of wavelength shift you observe. Okay, this is naturally there, and here you can connect the wave vector, okay, with lambda. That means you can connect lambda, so p and hk, so this k and p, they are connected, okay, as shown here. Fine. Okay, so this is known wave particle duality. Okay, yeah, this is exactly what I meant. Okay, so will not derive it. But we have this uncertainty. But anyway, whatever we have, we can try to find the standard deviation. And it turns out to be, if you take two operators, because you are doing two measurements, right? You are having uncertainty between two certain things. Okay. So if you take two two operators A and B, okay, this is the standard deviation, square of the variance, okay, meaning square of the standard deviation. Okay, that turns out to be that the modular square of expected value of this parameter. This quantity. This quantity is known as commutator. Okay, complicated, sounds complicated. Okay, let me simplify it with an example. I give you one matrix for A and another matrix for B. Okay, and if you want to know the uncertainty, you just try to find AB, you can do it, and BA, and try to find expectation value of this guy. You can do it. Now our things are matrix multiplication, matrix operation, and when you take the modulus of that, you get the result mathematically. This is the Heisenberg's uncertainty principle. But you have heard this uncertainty principle before, right? But you didn't see this expression. It doesn't look familiar. To make it familiar, take a couple of simple cases. Take operator A as x position, operator B as momentum. Try to find. Now you have seen this, right? So generally we write delta x, delta p. So in more mathematical way, it is sigma x and sigma p. So before that, you need to work out for this, okay, x and p. Please do it yourself, then you will actually know. So matrix I have told, but here, how do you find this operator? This is called commutator. Physically, what it means? Physically, it means that, so this is AB minus BA, right? But do you think that, so this is so here this operator means that I'm changing the operation sequence, right? Do you think if I change operation sequence, will the result change? May change or may not change. So I think I have given some problems, right? And just because I gave, I don't remember. But anyway, so suppose you take two matrices. Do you think if I multiply A with B and B with A, will you get same result for all matrices? Sometimes you can, sometimes you cannot. Right? Do you agree? Okay, now let me give you practical example. Rotation. Suppose I am rotating something, rotator operator you are already familiar with. I am rotating, say, 30 degree. I have one rotator operator 30 degree in plane. I have another rotator operator 60 degree. So I rotate something 30 degree. I rotate again 60 degree. Finally, how much rotation are we having? 90. Now changing the sequence, so that is, say, AB operation. Now if I do BA, what do? First you rotate 60 degree, then you rotate 30 degree. What is the final result? So what is the conclusion? These two operators commute. Okay. Now I think these are also included in exercise or homework problem. Okay. Now say we are doing same thing in 3D. Suppose we rotate, okay, in plane phi rotation, I have that operation, and then we rotate out of the plane 90 and 90. Okay, let's do things counterclockwise. So our vector here along x, we rotate, x becomes y, and if you rotate, so it becomes z, right? Now do it other way around. First rotate out of the plane and then rotate in the plane. You will see they are not commutating. Anyway, so there are two ways. Either you can bend your hands, you can bend it enough such that you become like Michael Jackson because you do it. Or, I mean, you figure out the matrix elements, right? Okay. Anyway, two examples. In one case it was commutating, in another case they're not commutating. Okay, now here, so you know what is the so x is x. Now it's x frozen. Okay, try to find this one, xp. How do you, if I give you matrix, it's simple. We'll just do multiplication, right? But this is in a function form. P is, how is P defined? Minus I h bar. Okay. So okay, do one thing. Take, okay, I lost my pen actually. So okay, so do this. So take this operator. Okay, so x p. So take a function f. Do it. So essentially what you will do, x p f minus p x f. Right? So here what is p? Okay, so now it will work on both this guy and this guy. Please do it yourself and let me know what you get. Do you get this result or not? So this is the derivative when it works on x. So what you, yes, you get constant, right? You get I h bar f, right? You get I h bar f. Is it okay? And when this guy is working on f, so you get x del f by del x. Please do it yourself. What are you getting? So what are you getting? So if I'm doing x p f, so there you'll see that there are factors which will be cancelled out. So here, are you getting like this times f? Sorry, it is a bit messed up, but right? Because the other term is getting cancelled. Are you getting it or not? Are you with me? Simple partial difference here, right? So that means if I take this f out, so x comma p, okay, so it will become I h bar. Is it okay? Everybody?
P is negative and there's
Maybe I just do it here, okay? That's not easy. Or maybe someone from audience can come and do it. We don't have much time. Quick, quick, quick. But anyway, in the meantime, still you work on this, okay? You don't have chalk.
Just take the x because p is the px, py, and pz because.
Yeah. Only take yeah px. Yeah.
So take just put again. So it's like x minus x. Let's get it there. So x if I just multiply here x f
Okay. Right.
px equals to minus I h bar, then let's I just put it on here. So x x minus I h bar divided by x if this minus
Maybe you can split two terms. Okay.
yes
Okay.
divided x this is the x if here. So just term out.
Okay. Just to work on the second term.
Yeah.
Yeah.
Minus I h bar x del f by del x. These things minus here minus I h bar and just partially derivative these things. So first dx from x is the 1 and then plus del x.
Maybe next line.
Del
They are not able to see.
del x. So if I just multiply this minus inside that, so it will become plus, here plus, it will become minus. If I just inside out the bracket, so minus I h bar also be there. Plus I h bar.
There's a sign issue somewhere.
Yeah. Here I h bar also there. So this two term is cancelled and only the I h bar, oh obviously f is there, f this is f is there, so f is there. So initially we started with x, px, f cancels.
Okay. Everyone did the same? Very good. So now you know how to find out this commutation. Okay. One simple. Maybe some others I have given in the home as a homework problem. So I'm sure you can work out. Okay. Okay. So now the thing is, okay. So then we have a particle. So what kind of waveform we like to define? Okay, well, I mean, such that it just, I mean, doesn't blow up. Okay, so what it turns, I mean, such that the uncertainty is minimum. It turns out to be that if you take Gaussian, okay, if you take Gaussian, then you can get the minimum uncertainty. I'm not proving it, bit lengthy proof, but you can verify it. Okay, just for sake of example. Okay, that concludes the first part. Okay, the fundamentals. Now our job will be solving the time independent Schrodinger equation for different potential profiles. Okay, so first one is a classic which is known as infinite potential well. So it means that here this is some sort of well. So within this well the potential is V equals to 0 and outside of that it is infinity. That means this particle cannot escape from this potential well. So it is kind of trapped. Okay. Okay. Now we need to solve Schrodinger equation for this case. Okay. The first thing is that we write down the Schrodinger equation. So it is expected that outside this, okay, we won't have any wave function because it is infinite potential barrier. It cannot escape. So whatever we have is within this well. So this is the Schrodinger equation, if you recall. So potential is 0, is considered to be 0 here. Okay. Now this is a simple second order differential equation. You can solve it. Right? Simple, right? So if you solve, what other things you get? You get sinusoidal, right? Something like that. This is very well known. Okay, second order differential equation. If you solve this equation, you get this. So you get this constant. This constant is this. Okay. So already you can see the relation between E and K, energy and K. Previously I said that K is related to momentum. So EK relation is emerging. We will see it will play a very important role in this course. Okay. Now what are the goals? We need to figure out these coefficients, right? So this is the system. We want to solve Schrodinger equation to know two important things. One, wave functions, meaning eigenvectors, another is eigenvalue, energy and wave function. That's all right. Okay. Yeah. So now we can get that using boundary condition. So at x equals to 0, wave function should vanish. Okay. So continuity of wave function at x equals to 0. So if you put x equals to 0, what do you get? X equals to 0, this is vanished, but we have this, b should be 0, right? B should be 0. So b is 0. So that means it is slightly simplified. So this is the solution. Okay. So we have another boundary condition, x equals to a. If you have x equals to a, what do we get? So at x equals to a, this should also vanish. That means Ka should be n pi, plus minus n pi. Okay. So now we get some relation. This case, this value of K is the spacing. Okay. The value of K cannot take any arbitrary value. It should be even, multiplication of pi, right? Already E versus K known. So if you know K, then you will know energy. So if I put this back here, we get the energy expression. Is it clear conceptually? Yeah.
X equal to 0 and sin 0, sin 0.
Yes, x equal to sin 0 is already there. That means psi to be 0. Sin pi is 0. So this b should be 0. So that's the thing. Yeah, so b should be 0. That's why I dropped this term b. So the wave function becomes psi is sin kx. Okay. Yeah. Now we do the same for x equals to a. And when we are doing it, we get the relation. We find expression of k. And previously we knew expression of E in terms of K. So now we get expression of energy. Now this is remarkable. The reason is E is proportional to n square. And we have other constants which are fine. So n is integer. It will be 1, 2, 3. What does it tell you? You cannot have continuous energy. Discrete energy, discrete allowed energy levels. Okay. So these are the things we have already discussed initially. Okay. Energy quantization. You have seen the quantized energy of our photons, quantized energy for electrons, Bohr's. Same thing you are also finding here. So this is a classic example where you can relate and appreciate this energy quantization. Okay, so particle in a box or in this infinite potential layer cannot take any arbitrary energy. It is quantized. So you get this concept of quantized energy. Clear? At least one problem is solved. So we know there are different energy levels. Okay. Point number 1. Now this is also important to our semiconductor, because right now we have discrete energy levels. Later on you will see discrete bands. Okay, from discrete energy levels we will get into discrete bands. Okay. Now what's our job? To finding wave function, right? Okay. So how do you find this wave function? We have used, there are weapons. Okay, we have used continuity of wave function. Later on we'll also use first derivative of that. There is another important thing, first postulate, normalization. It should be normalized because you need to find amplitude. That's all. Then normalize it. In that bracket notation, it was simple, right? You have seen matrix multiplication. You are already familiar here, and this is a continuous function. So how do you normalize? You take this integral. When we are doing matrix multiplication, it is discrete. And this is same thing in continuous, right? This is same as like you should have, I mean, this summation versus integration, that's all. Okay? Now, if you do this integration, sine square kx, I'm sure you can do it. Although it runs for minus to plus, but you should do from 0 to because other part it doesn't matter. I'm sure this is very simple integration. Even I mean, 10th, 11th students can standard student can do it. It is 1 by the first postulate. It cannot be more than 1, less than 1. Yes, that is a. I mean, here I'm showing how to use that, how to use this power. Okay, so here now we get this coefficient. Okay, now what is the full story? What are the possible? Again, you need to always relate to this eigenvalue problem. What are the different possible energy eigenvalues E1, E2, E3 and corresponding eigenstates, right? You need to put N1, 2, 3. Let's put everything together. It will look like that. So we will have ground state, first excited state, second, and so on. Note that this gap is increasing because E is proportional to N square. As you increase N, the gap will keep increasing. Point number 1. Point number 2. So this sine n pi by a, it will look like that, just like pulling a guitar string. Two ends are fixed. If you pull from center, it will look like that. The second one will be full and it will just go on. Okay, this is evident from this. So these are the possible eigenstates, right? Then the final point, what is the total combined wave function? Remember, we defined a vector in terms of C1, U1. So these are the basis functions. Okay, all of them. But I have to convince you that these are the basis functions. How? Because anyway, one is that they are eigenvectors, but anyway, you can also check. You can multiply taking n1, n equals to not multiply. Here we are doing inner product or this overlap integral. So if you do the same, like sine n pi on n pi, you will get value, or for any other case, they are orthogonal. Okay, here I mean it will be evident. Like this is the positive part, right? So plus and plus, if you multiply, it becomes plus, and here it will become minus. And eventually, if you, okay, yeah, you're getting this point, right? That means these are eigen states, and of course, they're orthonormal. This orthonormality is maintained by this, okay? That means the total wave function is sum of them. And we have some coefficients. These coefficients are basically saying, suppose I give you particle in a box and you do a measurement, meaning you want to know what is the energy at that moment. There are many possible outcomes. That means if you do at some instance, you will measure one of them. And this C1 corresponds that probability. Okay? Is it fine? Now you know if I give you one potential profile, how to solve this. Okay? Okay. Any question? Conceptual question. Maths thing you can check. Okay, because I mean, so with this slide, so maths thing you can check. But anyway, although it is a trivial, but you can check. But conceptually, so we have the wave function. I talked about continuity of wave function at the boundaries, then normalization, yeah, then solving energy values and eigenvectors. That's all. Okay, simple, clear. Okay, so now you get the flavor of energy quantization. Okay, now much simpler problem, which is free particle. Two extreme cases, right? Okay, so so one is like free particle is like democracy, freedom of speech and doing anything, and the second, the previous one, imposed. Okay, so free particles. So does real democracy exist? You will see now. Are you completely free? Never. Are you completely free? You're not free? Okay, we'll see whether you can be truly free or not, fundamentally. Okay? So, what is the potential for the free particle? Zero. You can go anywhere. You don't need any visa to travel anywhere. That's what free particle means. Okay? So, equation is much simpler than the previous. Okay? So now there are no boundary conditions. So previously we had boundary conditions, there are no boundary conditions. So that means we have these wave equations. What does it tell you? So one is forward moving wave and another is backward moving wave. Previously there was a restriction. There was a restriction and we had the consequence of that. Now no restriction like wave. Okay. So here I just want to also bring this time dependent part just to recap that. Okay. So this is the trivial phase part I mentioned. If you forget, it's okay. This is the simple part. Okay. Just multiply it. If you multiply, you get these two terms. Is it okay? So already we have something related to ikx. See, this is ikx. And we have this part, okay? So this is slightly changed, shuffled, okay? So we had two parts. So one is representing forward moving, another is backward moving, two waves, essentially. Okay? So I just want to rewrite it, okay? So we have k. It seems that if I can write it in this way. So essentially, I can have this k index. So this k is plus here. Okay, and then you will get this term, and this k is minus here, and then you will get this term. Do you agree or not? If k is plus, okay, k is, so here k is plus k, then you get exactly this term. Yeah, and if k is minus, then do you get this term? Right? Okay. So yeah, the ck plus, I mean c plus k is a, c minus k is this. Okay, I'm just making it concise. Is it okay? Okay. So now this is a wave equation, classic wave equation. So when you have it, you know the velocity. What is the velocity? So it takes this x minus vt form, right? So this is the velocity. If I give you a wave equation, you know what is the velocity. So this is the standard form of ikx minus omega t sort of form, right? So this is the velocity. You have this velocity coming from this. You okay with that? Okay, now these are the free particle, like free particle meaning a classical particle. I can do anything, I can go anywhere. Okay, so meaning my energy is all kinetic energy, no potential energy, half mv square is half mv square, meaning half p square by m. Okay, so from that I can have the relation between p and m. Do you agree? So the classically, this is what velocity would look like. E is half mv square, so root over 2e by m will be the velocity. Do you agree? Simple, right? But they are different. What is the case? What is the matter? Huh? So, okay, we'll see. Meaning, when you are free to do anything, there will be problem. Okay, so I mean, problems are about to come. Okay, too much of freedom here. Okay, so that's one issue. Okay, next thing is that in quantum mechanics, I said the wave function must be normalized. So this is a simple wave. Can you normalize it? Previously we normalized, right? Can you normalize it? This is a wave, right? Sine square. If you have single wave, you cannot normalize it. In signalization systems, you must have studied energy function and power function. What is it called? Energy function, right? You have said energy signal, power signal. Sine cos, this will be the power signal. Because energy is infinity. Because if you integrate, you cannot normalize it. Right? We represent in terms of power. That's even bigger problem. Suppose you and I have different opinion on any views. That's still okay. You are saying some velocity, that's not good, but anyway. But here we are not able to normalize. Okay, that's a problem. So that basically says that so-called classical particle, whatever we had, v equals to 0, it just cannot exist in quantum mechanics. Forget about it. It just cannot exist. Because it violates the first principle. Because the moment we have classical particle, it is free in space. That means position is not well defined. Like it is there everywhere, like God. Although we can quantize God, you know how to quantize God? Someone. So we will have jokes time to time, okay, to wake you up. What I mean by quantized God, we can have quantization within quantization. Okay, different ways of interpretation, of course. Okay, first of all, we can quantize based on religion. Define in number of religions, in number of quantized version of gods. Now, within a religion, we can have different powers, capability of gods. Okay, okay. I actually forgot why I said, but anyway. Uh, okay, so this classical particle cannot exist in quantum mechanics. Okay, so that's the issue. Fine, in quantum mechanics doesn't like a classical. Fine, it's okay. But particles exist, right? Particles. So how do you define a particle? What is the way approach? Okay, suppose I need to construct wave function. How do you approach? Approach is already we have the hints here. Okay, so now here, so the issue is we had a single frequency with a single amplitude. Anyway, we are running plus and minus. I know you understand positive and negative side of frequency or momentum, right? That you understand. Okay. But we have one amplitude. What if we have variation of that? Let's diversify the risk. Okay, that's how insurance works. Okay, let's diversify the risk. Okay, instead of having one wave function, let's have many wave functions with different coefficients. Such that if you do it, then eventually you will be able to normalize, because if you have many wave function and superposition of that, you can definitely find something like this, which will become 0 at infinity, because you will add things together such that it will do it, right? What I mean is the following. So here I'm just having the integral domain. Okay, so what I'm saying is that we can have C1 function of K1, C2 function of K2, so on. Okay, and if you don't want that summation term, we can convert that in integral. So that C, the coefficient function of K is this one. The remaining part function of A is this part. Okay, we just vary it continuously. Now this is interesting because you have already seen this type of expressions. And particularly electrical engineers get very excited. So now let's put t equals to 0 to simplify it. So they are nothing but Fourier transforms. Direct to reciprocal, reciprocal Fourier transform and inverse Fourier transform. Okay, this is how you can construct. Okay, let me give you one example. So you can construct it in the following way. For example, so my wave now looks like this. So I have taken 5 or n number of small waves. My way, your wave might look different. That is fine. That's not an issue. That's not a debate. Okay. The thing is, I can have some localized function like that. We call it wave packet. Previously I said that. So the Gaussian one, you can take Gaussian one. Wave as a Gaussian, because so if you do Fourier transform, that is also given in the exercise problem. I hope I have recorded by the way. So if we take the Fourier transform of Gaussian wave, Gaussian function, you get Gaussian, right? Okay. Yeah. So that's what I mean, like wave packet. So within wave packet, there are n number of possibilities, but they have defined probabilities such that they are now normalized, because so at x, this wave is almost died down, right? That means we can normalize it. At infinity, it is not blowing. we are able to normalize it. So suppose at t equals to 0, the wave packet is now residing here. Now after some time t equals to t naught, it will evolve and it can travel from here to there. Okay, now so here the problem was that the wave was entirely everywhere, but now we think that in terms of packet, as if the packets are moving. But this packet is not like this type of duster, I mean this type of remotes, okay? It is some sort of combination of waves. Okay, the velocity by which the packets are moving called group velocity. As a group they are moving. Okay, but within a packet there is a wave. Okay, and it has some velocity. You can define some velocity because we call it phase velocity. Now if you try, now you can connect this group velocity and phase velocity to this. So whenever we had this Vk, whatever we picked up here, that represents the phase velocity, and whatever we had here, that represents the group velocity. So this group velocity is defined d omega by dk. Okay, so there is in general small change. Okay, small change of this packet. Okay, in position. Is it clear? So let me just summarize. Okay, in one or two sentences. Okay, first thing is that we started with free particle. We got into trouble. We found plane waves. The issue is delocalized in space or time, but we don't know. Yeah, that's the issue. We couldn't normalize it, and we used this Fourier tricks to normalize it, and then we defined some sort of packets, and essentially we will like to see how this packet is moving. That's all. So now for a fundamental particle, when it is electron, you can think about this type of packet. It is neither billiard ball sort of thing, nor that type of wave, okay, that you imagined before. Some sort of packet exists there. Okay, so this gives you concept of wave packet, group and phase velocity. That's why free particle is very important. Okay, so in the class your idea should be understanding, because here also I'm typing, so I'll also provide you with these notes, and in textbooks you'll find. Okay, but anyway, for your ease I will provide you with the notes. Okay, I'll post it. I try to post that today. Okay, so free particle. Then third point. Okay, third point is, and then we'll wrap it up. So third point is potential barrier. So okay, see chronology Sanji. See what we had infinite potential well. That made your life easy because things were infinite. Free particle gave you something. Okay. Now this is important for electrical engineers because here you will see the tunneling effect, and that will come. Okay. 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 So what do you mean by finite potential barrier? So we have a barrier, say 0 to A. Within that, the potential is finite, not infinite. Okay, finite. And now we are taking a case, a particle having energy lower than the potential energy. It can also be higher. We are not considering this case here, but that you can work out. Okay, we are considering energy of the particle E lower than the potential barrier. If that is the case, then classically you cannot overcome the barrier, right? You cannot overcome the barrier because your energy is lower than the barrier. How can you overcome? But quantum mechanics, you will see that very soon there is a finite probability. That is the most striking feature. Okay, so now we have this profile. We need to solve again same thing. Potential is given. We need to solve Schrodinger equation. Okay, for different, now we have two cases. I mean three boundaries. Here inside side three regions actually, region left, middle and the right. Okay, and one thing, yeah, so this is how, okay, previously we defined wave vector. We have only one case, so now wave vectors to be defined inside the material and outside the material. Okay, simple maths. The way we defined earlier, we are doing the same thing. That's all. Okay, one thing and just slightly modify, and you will understand why. So we can define, see, eventually it is, you can think, anyway, even all the wave packets, you can think the wave packets coming, if it is wave, it will come, it will reflect, it will penetrate, right? So if we take these ratios, okay, modulus b by a whole square, you get reflection coefficients, right? What is incident, being incident and reflected. And if you take this E by A, then you get transmission. Okay. Now what we like to see in this case, whether this, what is the expression for this T, transmission and reflection? If you know one, you will get another one. Is this okay? So it can become zero, but that is what we want to find. Okay. How? Same strategies. So continuity of wave function. So how many wave functions we have? 1, 2, 3, 4, 5. Why? Because this is an incident wave. Some part we assume, you can always assume more initially. Okay, let the equations evolve, let the constant be 0 later on. But initially it should be normal, generalized. Okay, incident wave, reflected wave, and something also enters here in this region. Again, good to have two different signs, because we can work out what happens with C and D. Okay, these are the two possibilities. But here only one, because nothing is reflecting. So once it is in this side, it will just travel. Okay, so there is no good that we have 5, not 6. Okay, so now we need to do continuity of wave function here, continuity of wave function here, and another thing is important, that is the continuity of the first derivative. Okay, so if I do if I do continuity of the wave function here, you will get this. Okay, so put x equals to 0, a plus b becomes c plus d. Okay, fine. Okay, put x equals to 0, a plus b becomes c plus d equals to c plus d, and you can do the same for x equals to a. Okay, so this is the continuity of the wave function, and now you can take the derivative and do the same. Okay, you can do it later, but this is a process. You should understand what is happening. Okay, because I'm sure you can take the derivative, right? And this is what you will get. You should do it and tell me later if there is any mistake here. Okay, but this is fine. So now we have 4 equations, but unfortunately 5 unknowns A, B, C, D, E we can't solve. But we don't need to solve for all unknowns. What we need to know, B by A and E by A, right? So that you can do. So 4 differential equations, it looks a bit ugly, so we'll not do it, but you know eventually how to do it. Okay, it might take you like 10 minutes, 15 minutes, 20 minutes, or it may take 10 seconds, right? You can use Mathematica, or probably you will not do it. You just ask AI to do it and get the result, right? Okay, so finally, this is what you will get. Don't worry about the expression. This is what you get. Important thing to note is that T is the transmission probability, right? That is not 0. That is a striking thing. What are there? It will come mathematically. That you can derive. That's fine. We'll delve into that. It's okay. But the thing is that it is not 0. That's the striking thing. That means there is a finite probability that we'll have the particle this side, which is classically forbidden. We call this phenomenon tunneling. Clear? Conceptually, is it clear or not? Don't worry about the overall expression, because you can derive it. That's not an issue. But whether you are understanding or not, getting the essence. Okay? Now the next point is, what are the things it depends on? For example, what does your intuition say? If the barrier is thick, whether you will have more probability or less probability? Less, right? See if it is making sense here. Where is A coming? Here. So you need to know how sine h square function looks like, right? If it sounds a bit complicated, I can simplify it for you. You can see how it looks like. Okay, I'm just writing the final answer. Okay, so you can simplify this, and finally you will get this, because you can write, write how to represent sine x. Sin S becomes X when X is small. So the thing is that how sin A square becomes, okay? Anyway, you can see, okay, these are the mathematical things. So this is the final result. Okay, now easy to appreciate. So if A is increased, tunneling probability decreases. And not only just simple linear decrease, it will decrease exponentially. That is very important. That means if you slightly make it thicker, tunneling probability drops quite substantially. Does it make sense? Okay. And also in this term, you will find the V naught. Okay, higher the V naught as compared to E, lower will be the tunneling probability. Okay. So there are a lot of mathematics here that you can work out. I'm typing in, you will get the note soon. Okay. Conceptually, is it fine? This is not different from the particle in a box. Slightly complicated mathematically. Okay, meaning you need to solve many equations, but same process is same, and outcome is striking. Striking enough for everybody? Striking enough? Okay. Yeah, these are the three important things that I feel like we should discuss in class because they give different perspective. Okay, first one gives you energy quantization, really energy level quantize you experience. Second one gives you very important understanding of wave packet and how it moves. Third one is related to us, just slightly complicated example. Okay, how tunneling, because you will encounter tunneling, yeah, but there are many variants. For example, instead of have finite potential barrier, I can have finite potential well. You can compare what happens if the potential well is infinite versus finite. Okay, there are other possibilities in semiconductors. You will find lot of dopants, defects that can be represented delta potential. Okay, we can have step functions. You can imagine all different functions. And most importantly, you will find triangular potential well. Because you are from MTech and PhD, so you have already studied a little bit of MOSFETs, right? MOSFETs and MOSFET. So this kind of triangular potential profile is very common in semiconductor. Okay, because that always happens. And if you go into heterostructures, like whoever working will be working on gallium nitride 3', this is evident. Okay, this kind of quantum wells are there already. So you need to know how to solve. We'll not solve all of them, but we give you enough foundation how to do it. Okay, next step will be I'll post the notes, some homework problems, and now slowly assignment problems will come. Assignment or mini project, whatever. So in that you will see you need to work out. You need to do some simulation. For example, I'll give triangular potential well. Okay, maybe expressions will be difficult. You'll solve it analytically. You'll solve it numerically. Generally, I allow people to use AI, no issues, but you should understand. Okay, okay, you should grasp it. Okay. Okay, another thing, so finite potential well we have, but later in the next class we will see that when we have many finite potential wells together, actually we are in the regime of, we are stepping into lattice. Okay, and we'll discuss a chronic PME model and you'll see how energy bands evolve. So previously you have seen the quantization of energy states. Later you see energy bands. That's why this is important. Okay. Yeah. So let me. Any questions so far? Conceptual.
Sir, you were thinking that normalization was the same as like having the total probability equal to 1, but sir, the probability one is like sigma of that Ci square equal to 1.
Yeah. So that is a discrete version. That is a summation if it is in discrete domain. If it is continuous domain, that will become like integral.
It contains all the
Correct.
Ci.
Correct.
Whether we are integrating and integrate this one. So how is it?
The process is same. So when we are you are doing matrix multiplication, also you have basis functions. Okay, so they all, I mean, So when we have ui and ui, I and I, okay, you get values there and you get the corresponding coefficients, say C1, C1. For other terms, it becomes 0. Same here. So when we have in a continuous domain, sine say kx, okay, when it is multiplied by sine kx, you get the coefficients. For others, it is naturally gone. Say sine kx, sine 2kx. When you take that integral, it is naturally gone. But in principle, when you are doing, you just do for all the steps. But I mean, that's the essence. That's how we define the basis vectors such that other overlap integrals will become 0. Only coefficients matter. Okay. Okay, let me just stop. I'm a bit worried.